Hi, in this video, we are going to look at standing waves. Now, standing waves is an interference pattern where waves actually move in one direction and then they reflect it back and make a pattern which appears to be stationary. So for example, if you have a piece of string in your fingers and you just spin it, pattern may look like this one. So these points which don't move at all, these are called nodes. And the point which move with the maximum displacement, so string will be moving with the maximum displacement, these are called antinodes, and so on. So if you notice that this end, which end of the string which was held in your fingers, and what you're doing is you hold up string and you just spin it and that pattern will be formed. So over here, there is a node. So the rule is that a fixed end will always be a node. Now this end of the bottom end of the string is free, and that will be always an antinode. Now dotted line shows that string is moving from this position to that back and forth. But because they move so fast, to naked eye, it looks like string is not moving, and that's the pattern, and that's why they're called standing waves or the stationary waves. Distance from one node to another node is half of the wavelength, or one complete wavelength will be like a one crest and a one trough, which is from here to there. Now, what's the difference between a standing wave and a traveling wave? So in a traveling wave, if the wave is traveling in this direction, particles move down and then they move up. So this particle will be moving as the wave up and down as the waves go past it. Whereas in this one, in a standing wave, all of the particles over here, they're all moving together downwards, whereas the second part, these are moving upward. So and then these are here, and then after half a period, they will be there, and after one period, they will be back there. And from here to there is one complete wavelength or one complete wavelength. Now let's look at the standing waves that are formed in strings like piano or guitar instruments. Now, the basic principle of any wave that is traveling is V equals F lambda. V is the speed of the wave, F is the frequency, and that is the wavelength. Now, in one particular string, speed will be fixed. It depends on the tension in the string, weight of the string, and so on, but it will be always, speed will be same. However, if the frequency of the spinning or movement of the string is changed, then pattern will be changed. So the lowest frequency, where string moves like this one, so these 2 points are the nodes, and this is the antinode. So that's called the first harmonic. So in first harmonic, wavelength of this particular pattern is twice the L, because from here to there is half a wavelength, so wavelength is twice the L. So what you will be asked is calculate the frequency. So if you have given the speed and you're given the length, you can calculate this one. And using the equation V equals F lambda, you can calculate the frequency. Now in a string, both ends are fixed. So there will always be a node on the fixed end. So if you increase the frequency, then second time you will see what we call as resonance, or the string will be moving with the maximum amplitude. The pattern will be like that. So node, red ones are node, blue, yellow ones are antinodes. So that's the second harmonic. And how much is the wavelength? Wavelength is from here to there, that's equal to L. And if you're given the speed, you can calculate the frequency. And that's the next pattern and the next pattern. Now, what's the relationship? Frequency 2 is 2 times the frequency of one, first harmonic. Third harmonic is 3 times the frequency of that one. And fourth harmonic is the 4 times the frequency of that one. So these are the patterns that are seen in all the string instruments where both ends are fixed. Okay. So that, as I mentioned, if you want to find the fifth harmonic, that will be 5 times the first harmonic, F1. And basic equation is V equals F lambda. Now, first of all, now we will look at standing waves in air columns. And standing wave in air columns, and air moves always, and it's a longitudinal wave. So sound waves that produce in pipes are longitudinal waves, but it is easier to draw them as transverse waves. So say, for example, if someone is making some sound from here, sound waves will travel there, they will reflect back, and they will make a pattern. So this is the first harmonic, or it's called fundamental. So the fixed end will always be a node. That's the free end or an open end. So a closed pipe is the one which is closed at one end and open at the other one. So from here to there is quarter of a wavelength. So wavelength will be 4 times L. So if you need the speed, you can calculate the frequency by using V equals F lambda. Now, next pattern in the closed pipe is, now this one will have to be always an antinode. So pattern cannot be like that, where you cannot write like that. So what it means is that second harmonic is not possible, or it does not exist in a closed pipe, because this will never become a node. So air will resonate only. The next pattern will be, there will be a node here, an antinode there, an antinode over here. So this is half a wavelength, and that's a quarter. So this one, the wavelength from here to there is 3/4 of the wavelength. So wavelength will be 4/3L in terms of length. So in these questions, what you have to do is you have to be able to calculate the wavelength in terms of the length of the pipe. Once you've calculated the wavelength, V equals F lambda. If you're given the speed, you can easily calculate the frequency. So, so first harmonic, this is the third harmonic. Second harmonic does not exist. Neither does the fourth harmonic, because in the fourth harmonic, that it will be, this pattern will be over here, and that's not possible. Fixed node cannot happen at the open end. So the next pattern will be fifth harmonic, and wavelength is 4/5L. Wavelength is from here to there, and there are 5/4, so it's 4/5 of the length. So you can calculate the frequencies. So third harmonic will be still 3 times that one, or fifth will be 5 times the first one. So these are the patterns for the closed pipe. Now, open pipe is the one which is open on both ends, and open end can only be an antinode. So there will be node in the middle, antinode at the end. So this is quarter of a wavelength, another quarter making it half. So from here to there is half a wavelength. So wavelength will be twice the length of this pipe. So that's the first harmonic. Second harmonic will be, now when we draw these patterns, you always have to say that number of node increases in each pattern. So in this one is 1, second one is 2, next one is 3. And remember, open end will always be an antinode. It was the same rule here. First one has got 1 node, second one has got 2, third one has got 3 nodes. So in this one, because there will be open end will have to be an antinodes, antinode, 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 node, and node. If you look at the total length, this is equal to half a wavelength from here, quarter there, making it 1 full wavelength. So if you know the wavelength, then we can calculate the frequency again by using frequency is speed divided by L. And that's the third harmonic. So in open pipe, there will be first harmonic, second harmonic, third harmonic, and third harmonic will be 3 times more than that. So closed pipes are slightly different, but these ones have got similar patterns as over here. Only difference is in strings, both ends are fixed, so there are nodes at the end. And in pipes, open pipes, there is antinode at each end. So all these questions will be involving, this is just a summary of all the same patterns again. So in these questions, you will be maybe asked to draw the patterns, calculate the wavelength in terms of the length, either for a closed pipe, open pipe, or a string, and then calculate the frequency. So that's all for this video. Thanks for watching it.